shape. And that's exactly what I want to first think about is here is the collection of some of the primes that we originally saw. And I want to think about which of these primes have the representation of being a sum of two squares and which ones don't. So right away we saw that 3 and 7 and 11 all do not work. We also saw 5 and 13 and 17 do work. And at that point in time, you can actually already begin to see the connection being formed. If you think about 3, 7, and 11, they all share a really nice property when you begin to think about divisibility by 4. So 3 plus 4 more makes 7, 7 plus 4 more makes an 11, 11 plus 4 more makes 15, which is not prime. If I take the 15 and add 4, I'm up to 19. If I add 4 to the 19, I'm up to 23. If I take 23 and add 4 more, I'm up to 27. If I add 4 more, I end up at 31. And you can see that all of those ones were versions that it did not work. So it somehow seems to work and not work based off of this divisibility by 4, and in particular, what happens when I have a remainder of 1 mod 4 versus what happens when I have a remainder of 3 mod 4. So you can see that the ones that have a remainder of 3 mod 4 all appear to not work. The 3, the 7, the 11, the 19, the 23, the 27, the 31, all of those examples actually do not have this representation as a sum of two squares. Whereas the other ones, so the 5 and the 13 and the 17, those ones are all going to kick out a remainder of 1 after I divide it by 4. So the 5 does work. If I added 4 to that thing, well, I'd be up at 9, which is not prime, but also can be represented as a sum of two squares. If I add 4 to that, I'm up to 13, and that one works. If I add 4 more, then I'm up to 17, and that one's going to work. And you can begin to kind of run that process a little bit farther. And that's exactly where we're going to be at in our kind of big statement for this section, is that if you give me an odd prime, and I probably should jump back and say, we're only going to be really talking about odd primes. The number 2, yes, this does work, but I'm not going to think about classification underneath this kind of division by 4. So we're just going to be dealing with odd primes. So if you give me an odd prime, then I know that this thing is going to be represented as a sum of two squares if and only if. So this is a kind of biconditional. It goes both ways, is that if you have the representation as a sum of two squares, then you're going to be congruent to a 1 mod p. And more importantly, the other direction is true as well. If you are a 1 mod 4, I think I said mod p before, but if you're a 1 mod 4, then you know that this thing can actually be represented as a sum of two squares. So the examples that we just saw, the 5 does work, the 13 does work, whereas the 7 and the 11, those ones do not work. And that is perfectly fitting this overall classification that we see up above, is that this nicely divides all of our primes in half, essentially in half, as kind of saying which ones will it work for and which ones will it not work for. All right, so now I want to think a little bit about how are we actually going to show this thing. One of these directions is actually pretty friendly and pretty kind of easy if you think kind of back to your days of Math 201. The other direction is where the full meat of this argument is all about. So the forward direction is actually pretty nice. So if I'm going to assume that my prime p is going to look like an x squared plus a y squared, my goal is to show that this prime p is going to be a 1 mod 4. And the kicker here is that this prime is odd. If I have some odd number and if I represent it as two things added together, I know one of these things should probably be even and one of these things should probably be odd. It's the only way two things can add together to actually make an odd number. I can't have them both be the exact same. And that's exactly what's underlying this overall direction, is that if I have some even number and it's emerging from some number squared, it had to emerge from an even number. So think about taking your favorite even number. If you square it, it's still going to be even. If you take your favorite odd number and square it, it's still going to be an odd number. So that's kind of our classic Math 201 results, is that if you start with even and oddness, if you square these objects, they tend to stay in that camp as well. What you can also do is you can actually extend it just a little bit. You don't have to be living in just the kind of mod 2 world of this kind of even and oddness. You can actually extend it all the way up to a mod 4. And the idea here is that maybe my prime p looks like some even number squared plus some odd number squared. So I know one of them has to be even and one of them has to be odd. Let's just assume the first one is the even bit. If you square that first number, it's going to emerge as a 4k squared. So hopefully you can see that that's going to be a 0 mod 4. And if I square the second little bit, it's going to become a 4l squared plus a 4l plus a 1. So if you stare at that thing long enough, you can see that all of this stuff is going to emerge as a 0. So at the end of the day, this thing is just going to become a 1 mod 4. And hooray, we're done. That shows us our forward direction, is that if you take this prime p, it's going to then be represented as a 1 mod 4. There's actually a little bit more behind the scenes here, is that if you give me any odd number, what's going to happen is that if I view it mod 4, it's either going to be a 1 or it's going to be a 3 mod 4. So what ends up happening is that if you look at objects that are squared, they can only emerge as either a 0 or a 1 mod 4. And if I add a couple of these things together, there's no way I can add up to a 3. And you can see that that's actually this argument down here, is that the even number squared emerged as a 0 mod 4, and the odd number squared emerged as a 1 mod 4. So if I add those two things together, here we can see that it added up to a 1. If you took two odd ones and added them together, it would emerge as a 2. If you took two even ones, added them together, it would emerge as a 0 mod 4. So there's a little bit of that kind of trickery that you saw back in 201, but really it's all the same stuff, is that if I'm taking this odd number, I represent it as a sum of a couple squares, and everything works out really nicely when I view this mod 4, in that the 3 situation does properly go away. So the meat of this argument, well, I guess if you want a slightly cleaner version, there's a cleaner version for you to look at. But the true meat of this argument is actually going to be going in the reverse direction.